Million state-of-the-art Airbus A320neos, some barely a year old, are being deliberately torn apart and sold for scrap. These are airplanes engineered to fly safely for 25 to 30 years. They feature the most advanced aerodynamics and fuel-saving technology ever put into a narrow-body commercial jet. Yet, they are facing the executioner's blade before they even need their first major inspection. Why? Because in today's broken aerospace supply chain, a brand new airplane is literally worth more dead than alive. To understand how the aviation industry reached this point of absolute madness, we have to look at the beating heart of the airplane itself, the engines. The Airbus A320neo, which stands for New Engine Option, is the fastest-selling commercial aircraft in human history. Airlines bought them by the thousands because they promised a massive 15 to 20% reduction in fuel burn. But that incredible efficiency came at a devastating, unforeseen cost. The crisis begins with Pratt & Whitney, one of the most legendary engine manufacturers on Earth. They developed the PW1100G geared turbofan engine for the A320neo. It was an engineering marvel, but in July 2023, Pratt & Whitney's parent company, RTX, was forced to make a catastrophic disclosure to the public and the financial markets. They revealed that a rare condition in the powdered metal used to manufacture certain engine parts was contaminated. This wasn't just a minor glitch. This contaminated powdered metal was used to forge high-pressure turbine discs deep inside the core of the engine. Because of the microscopic impurities in the metal, these discs were susceptible to micro-cracks. In the extreme heat and immense rotational stress of a jet engine, a micro-crack is a ticking time bomb that can lead to an uncontained engine failure. The response had to be immediate and severe. RTX mandated that thousands of these engines be removed from aircraft and meticulously inspected. The sheer scale of this recall is staggering. RTX officially projected that an average of 350 aircraft would be grounded annually through the year 2026. But the peak of this crisis hit in the first half of 2024, where an estimated 600 to 650 aircraft were sitting idle on the tarmac, completely engineless. Now, in a normal world, an airline would simply take the engine off, send it to a maintenance facility, and bolt a spare engine onto the wing while they wait. But we are not in a normal world. Before the global pandemic, a standard engine overhaul took roughly 60 to 90 days. Today, the aviation industry is suffering from a crippling lack of replacement parts and a severe shortage of skilled aerospace mechanics. Because of this bottleneck, the turnaround time for a Pratt & Whitney geared turbofan engine has stretched to an agonizing 250 to 300 days. In some extreme cases, airlines are waiting up to a full year just to get a single engine back from the shop. You might be thinking, surely the airlines that chose the other engine option for the A320neo are perfectly fine. But they aren't. The alternative to the Pratt & Whitney engine is the CFM International LEAP 1A. While CFM doesn't have a massive, headline-grabbing powdered metal recall, their engines are facing their own severe operational crisis. The LEAP engines run incredibly hot to achieve their fuel efficiency. As a result, they are wearing out much faster than anyone anticipated, particularly in harsh, dusty environments like the Middle East and India. The time an engine can safely fly before needing an overhaul is called time on wing. For the CFM LEAP, that time on wing is falling drastically short of expectations, because both engine types powering the world's most popular airplane are struggling simultaneously. The global shortage of new generation narrow-body engines has compounded into an absolute nightmare. There are simply no spare engines available. This brings us to the brutal, cutthroat economics of the teardown. When an airline has a plane sitting on the ground for 300 days, they are bleeding cash. They still have to pay the lease on the aircraft. They still have to pay the pilots, and they are losing all the revenue that plane was supposed to generate. Desperation sets in. Airlines are scouring the globe for spare engines to rent. Industry data from late 2023 and early 2024 shows that airlines are willing to pay upwards of $200,000 to $250,000 per month just to lease a single spare Pratt & Whitney or CFM LEAP engine. That is $250,000 a month for one engine, if they can even find one. This astronomical demand for parts and engines has completely inverted the valuation of young aircraft. Enter the aircraft lessors. It is a little-known fact outside of the industry that many airlines do not actually own their airplanes. They rent them from massive leasing companies. Lessors are financial institutions, and they are driven entirely by math. Normally, a lessor would never take a perfectly good, leased airplane from a paying airline to tear it down. But the planes being torn down at 1 to 5 years old usually have a specific catalyst. The first catalyst is bankruptcy. When an airline collapses, the lessor immediately repossesses the aircraft. Take the Indian airline Go First, which filed for bankruptcy in May 2023. In their bankruptcy filing, they explicitly blamed Pratt & Whitney, stating that the engine defects forced them to ground 50% of their entire A320neo fleet, choking off their revenue. When lessors repossessed these 2 to 4-year-old aircraft from Go First or from other collapsed carriers like Kia's Viva Air, they faced a difficult choice. They could spend millions of dollars reconfiguring the cabins, repainting the fuselages, and finding a new airline to lease them to. Or they could look at the desperate market for spare parts by tearing the plane down immediately. The lessor gets a massive, instant cash payout. The engines alone can be leased out for $500,000 a month as a pair, or sold outright for tens of millions. The landing gear, the avionics, the auxiliary power units, every single piece is worth a fortune to an airline desperate to keep its own fleet flying. The math is undeniable. The lessor makes more money, faster, by destroying the plane. The second catalyst driving this bizarre teardown trend is geopolitical. Following the invasion of Ukraine and the subsequent heavy sanctions, lessors scrambled to recover billions of dollars worth of aircraft leased to Russian airlines. While most were stolen by the Russian state, lessors did manage to recover a small number of young Airbus and Boeing aircraft. However, because these planes were operated in Russia under heavy sanctions, their maintenance records were compromised. In aviation, if you cannot perfectly trace the maintenance history of a part, it cannot legally be flown in the West. The airframe itself becomes a massive liability. However, individual parts and engines can be put through rigorous recertification processes and sold. This loophole has led to the teardown of practically brand new planes that escaped Russia, simply because their paperwork was tainted. But the teardowns are just one part of a wider, highly controversial strategy currently sweeping the industry. It is a practice known as harvesting green time. Green time refers to the remaining cycles, meaning the number of takeoffs and landings an engine has left before it is legally required by aviation authorities to undergo heavy maintenance. Right now, airlines and lessors are buying up or repossessing young aircraft, stripping the engines off the wings, and slapping them onto other airframes just to burn off the remaining green time. They are treating multi-million-dollar engines like disposable batteries. Once the green time is exhausted and the engine hits its legal limit, it is pulled off, tossed into the 300-day wait list for maintenance, and the airframe it was originally taken from is permanently sold for scrap parts. This entire situation has created a bizarre and paradoxical financial ecosystem. You would think that having hundreds of planes grounded would bankrupt the airlines operating them. But the manufacturer, RTX, is legally bound by contracts to pay airlines for what is known as aircraft on ground, or AOG penalties. If the engine breaks and the plane can't fly, the manufacturer has to cover the airline's financial losses. In the third quarter of 2023 alone, RTX took a massive $3 billion charge specifically to cover compensation to airlines. Carriers like Spirit and JetBlue are receiving millions of dollars in compensation from Pratt & Whitney for their grounded planes. This creates an absurd reality where an airline might actually be financially stabilized, or even propped up, by the compensation checks they receive for a plane that does absolutely nothing but sit on the tarmac. Meanwhile, across the world, lessors are tearing down identical planes to supply the spare parts market. The ultimate irony of this entire crisis, however, is the environmental impact. The entire purpose of the Airbus A320neo was to usher in a new era of green aviation. It was built to reduce carbon emissions by up to 20% compared to older aircraft. But because these young, highly efficient planes are either grounded waiting for engines or being actively parted out by lessors, Airlines still have schedules to maintain. They still have millions of passengers who bought tickets to fill the massive hole in their fleets. Airlines are being forced to resurrect the dead. They are extending the leases on old, gas-guzzling, previous generation aircraft, specifically the Airbus A320ceo and the Boeing 737 Next Generation. These are planes that are 15 to 20 years old. They burn significantly more fuel and emit far more carbon. But they have one massive advantage. Their older engines are incredibly reliable, and the supply chain for their spare parts is robust. Because of the crisis with the new planes, the value of these old, heavy polluting aircraft has skyrocketed. Lease rates for a 15-year-old Airbus A320ceo have surged past $200,000 a month. These are valuation levels that the industry has not seen in over a decade. Airlines are spending fortunes to keep these aging workhorses in the sky, completely stalling the aviation industry's highly publicized green initiatives. The new, clean planes are being ripped apart for parts, while the old, dirty planes are being flown harder and longer than they ever were intended to. What we are witnessing is a perfect storm of catastrophic proportions. It is a collision of highly complex manufacturing defects, premature wear and tear on cutting-edge technology, post-pandemic labor shortages, and a skyrocketing global demand for air travel. The aerospace supply chain has been stretched so thin that it has finally snapped, creating a reality that defies all traditional business logic. Until the engine manufacturers can fix their production lines, clear the 300-day maintenance backlogs, and prove that their new technology can actually stay on the wing, this madness will continue. Brand new, state-of-the-art airplanes will continue to be towed into the boneyards, stripped of their engines, and torn limb from limb, simply because in today's aviation industry, the parts are worth more than the plane.
The Airbus A220 is the ultimate passenger experience. It is whisper quiet, incredibly fuel efficient, and the undisputed darling of modern commercial aviation. But this flawless reputation hides a darker reality. This perfect jet completely bankrupted its creator. It loses between $1.5 and $2 million on every single delivery for the company that saved it. The physical and financial carnage left in its wake is staggering. Bombardier poured $6 billion into its development and racked up $9 billion in debt, permanently destroying its 30-year commercial aviation legacy. Flagship customers like Iraqi Airways and Air Baltic have seen entire state-of-the-art fleets completely grounded. How did the most loved, fuel-efficient passenger jet in the sky become a multi-billion-dollar curse that destroys the finances of everyone who touches it? The jet is full of bizarre anomalies. Early prototypes had takeoffs so quiet that aviation journalists standing by the runway thought the pilots had aborted, mistaking the engines for a large vacuum cleaner. It is a cutting-edge green aircraft that actively forces airlines to burn more carbon, and it was born from a state-of-the-art aerospace program that was eventually sold to a rival for exactly $1. The origin of this paradox traces straight back to the moment the A2000 fires. On May 29, 2014, at a ground testing facility at Mirabel Airport in Quebec, Bombardier test engineers are running a stationary test of the very first flight test vehicle. Suddenly, an uncontained explosion rips through the Pratt & Whitney engine. White-hot shrapnel violently tears through the engine casing and shreds directly into the composite fuselage of the aircraft. Fire crews immediately flood the tarmac. The physical cause of the blast came down to the engine's core architecture. Traditional engines have the front fan and internal turbine spinning on the same shaft at the same speed. This engine uses a 3-to-1 reduction gearbox. This allows the front fan to spin slowly, making it ultra-quiet and efficient, but it forces the internal turbine to spin incredibly fast and hot. That extreme thermal mechanical stress is exactly what just blew up the first test vehicle. The shrapnel from that explosion grounded the entire test fleet for over 100 days, proving the foundational technology of the aircraft was terrifyingly unstable. The engine was physically tearing itself apart on the tarmac, but a weaponized piece of paper from Washington was about to prove even deadlier than the flying metal. On April 27, 2017, inside the International Trade Commission headquarters in Washington, D.C., Boeing lawyers swagger in and drop a 134-page petition on the desk. They demand immediate anti-dumping tariffs on the Canadian jet, then known as the Series, following a major order from Delta for 75 aircraft. Months later, the US Commerce Department strikes, slamming Bombardier with a staggering punitive 2% tariff. The market mechanics of this ruling were an instant corporate death sentence. A $30 million jet now carried a $90 million tax. It mathematically bankrupted the program in the United States overnight. The plane was aerodynamically perfect, but now completely illegal to sell at a competitive price. Facing a mountain of debt, and permanently locked out of the most important aviation market in the world, Bombardier is hours from total collapse. Who would step in to save the dying jet, and what predatory price would they extract? On October 16, 2007, at a secretive signing table broadcast from Paris and Montreal, Airbus CEO Tom Enders and Bombardier CEO Alain Bellemare sign a contract. No billions of dollars change hands. Airbus takes majority control of the entire program. The final purchase price is exactly $1. Airbus pulled off the greatest heist in aviation history, capitalizing on Bombardier's desperate supply chain stranglehold. Bombardier had originally designed the jet without the massive purchasing power of Boeing or Airbus, forcing them to sign exorbitant locked-in supplier contracts just to get the plane built. Airbus inherited those exact contracts. They also weaponized the final deal through ruthless vulture clauses. Airbus used put and call options to effectively force the Quebec government, funded by local taxpayers, to absorb all program losses until 2026. Boeing's hyper-aggressive litigation had catastrophically backfired, literally gifting their worst enemy a total monopoly in the 100-250-seat market. But Airbus quickly realized those inherited contracts meant that Airbus swallowed a bitter financial pill to acquire their new flagship jet. But an invisible physical poison pill was waiting to turn this boardroom victory into a mid-air terror. On July 25, 2019, 32,000 feet over the remote forests of Pyrénées-sur-Marne, France, Swiss International Airlines Flight 3048 is cruising smoothly. Suddenly, a violent bang shakes the cabin. The left engine disintegrates internally. Flames shoot out from the exhaust. Shards of the titanium low-pressure compressor tear through the engine housing and plummet 32,000 feet into the French forest. The crew immediately face the engine glider anomaly. Because of the massive fan size and the gear mechanism, shutting down a geared turbofan engine in flight creates massive aerodynamic drag. This unpowered fan acts like a parachute on one wing, causing severe asymmetric handling issues for the pilots fighting to land the crippled plane. The danger had moved from test tracks and boardrooms directly to 120 passengers in the sky. This massive in-flight engine failure happened 3 times to Swiss Air in just 3 months, forcing the airline to ground its entire fleet. The engines were now exploding mid-flight. But what invisible microscopic defect was about to turn this isolated terror into a global shutdown? By July 2023, tarmacs around the world are lined with state-of-the-art A240s sitting dead, completely missing their engines. Turnaround time for routine repairs has jumped from 60 days to an agonizing 300 days. Executives at Pratt & Whitney's parent company step forward to reveal the devastating truth. Rare microscopic contaminants inside powdered metal used to forge high-pressure turbine disks between 2015 and 2015. This microscopic contagion finally answers how the perfect passenger plane became a financial curse. The combination of the geared turbofan's extreme thermal stress, the contaminated powdered metal, and the terrible inherited supplier contracts created an aircraft that is brilliant in the air, but economically and structurally fragile on the ground. This failure birthed the green lie of the A220. Because 2,000% of the global fleet is grounded due to engine shortages, airlines desperate to maintain their schedules are forced to wet lease 25-year-old, gas-guzzling Airbus A319s and Boeing 737s. The failure of this hyper-efficient, eco-friendly engine is actively forcing airlines to burn more carbon just to keep their routes intact. The engine manufacturer was forced to take a staggering $3 billion. The bleeding-edge chemistry meant to save the environment is actually destroying it, and the plane that was supposed to revolutionize aviation is instead permanently parked on the grass. Today, Bombardier has lost its identity entirely. An aerospace titan was stripped of its commercial legacy and reduced solely to making private business jets. Airbus is currently churning out highly demanded A2000 from factories in Mobile and Mirabel, but they are bleeding cash on every unit, praying to finally break even by 2026. The Airbus A220 is a prodigy. It achieved undeniable aerodynamic and acoustic perfection, but it proved that in modern aviation, bleeding-edge innovation is relentlessly punished by the brutal realities of supply chains, geopolitics, and microscopic chemistry.
You probably assume that when you board a commercial flight, the airline's ultimate goal is to get you to your destination as fast as humanly possible. Faster flights mean happier passengers, lower catering costs, and planes freed up to fly more routes. It makes perfect logical sense. It is also a complete myth. Airlines do not actually want to get you there as fast as possible. Deep inside the aircraft's flight management computer is a proprietary algorithm driven by a hidden number known as the cost index. This index, ranging from 0 to 999, mathematically balances the cost of time, like crew wages and maintenance schedules, against the ever-fluctuating cost of jet fuel. Here is the controversial truth. Even if your pilot plots a route that catches a massive, roaring tailwind, a wind so powerful it could shave 45 minutes off your total flight time, the computer will often automatically throttle the engines down. The airline deliberately uses that incredible tailwind not to get you home early, but to burn less fuel, arriving at the exact same scheduled time and quietly pocketing the financial savings rather than passing the time savings onto you. But despite this corporate speed limit, there is a fascinating, almost magical phenomenon hidden in the physics of modern aviation. Sometimes, airlines deliberately choose to fly hundreds, or even thousands, of miles out of their way. Dispatchers will intentionally ignore the shortest physical path, abandon the straight line, and chart a geographically massive detour. And yet, by adding all this extra distance, the aircraft arrives significantly faster. To understand why a longer flight path is routinely the quickest way across the globe, we have to dismantle the illusions we have been taught about maps, investigate the fluid dynamics of our atmosphere, and uncover the bureaucratic secrets of the sky. The deception begins with the map you are likely picturing in your head right now. Almost all of us grew up looking at a standard Mercator projection map, where the Earth is flattened out into a neat rectangle. On this map, drawing a straight line between two cities creates what is known as a run line. It looks like the absolute shortest distance, but the Earth is a sphere, and flattening it distorts the geometry of reality. In the physical world, the shortest distance between 2 points on a globe is called a great circle route, which looks like a massive, sweeping curve when projected back onto a flat map. You might think that airlines would simply fly this great circle route every single time. But aviation dispatchers do not route for distance. They route for time and fuel. This brings us to a revolutionary concept known as wind-optimized routing. Up at cruising altitude, between 30,000 and 39,000 feet, lies the tropopause. This layer of the atmosphere hosts the polar and subtropical jet streams. These are essentially massive, invisible rivers of kinetic energy, narrow bands of incredibly strong wind flowing west to east, driven relentlessly by the rotation of the Earth, known as the Coriolis effect, and the uneven solar heating of the planet. In the winter months, the core of these jet streams routinely exceeds 200 miles per hour. Airlines have realized that by deliberately extending the geographical distance of a flight by hundreds of miles, they can steer their aircraft directly into the core of these high-altitude kinetic rivers. Conversely, on a westbound flight, they will fly massive detours specifically to avoid a headwind core. To prove exactly how effective this is, a breakthrough mathematical study was conducted in 2021 at the University of Reading. Researchers analyzed 35,000 transatlantic commercial flights. The findings were undeniable. By utterly abandoning the shortest distance great circle routes and instead flying geographically longer, wind-optimized paths, commercial flights saved up to 16% on fuel and reliably reduced flight times by several minutes per trip. The math behind this is startlingly elegant. If an aircraft extends its flight distance by 100 nautical miles, which is roughly 115 standard miles, just to catch a 150-mile-per-hour tailwind, the net time savings is approximately 10 to 15 minutes compared to flying the shorter route with neutral winds. To visualize this, you have to understand the difference between true airspeed and ground speed. Imagine a swimmer in a river. True airspeed is how fast the swimmer is paddling through the water. Ground speed is how fast the swimmer is actually moving past the trees on the riverbank. If the river is flowing incredibly fast in the same direction, the swimmer's speed relative to the riverbank becomes massive, even if they aren't paddling any harder. This exact fluid dynamic principle created one of the most misunderstood and sensationalized moments in modern aviation history. On the night of February 8, 2020, British Airways Flight 112, a massive Boeing 747, took off from New York's JFK Airport heading for London Heathrow. Above the Atlantic, a ferocious weather system known as Storm Chara was fueling a hyper-accelerated jet stream. The flight dispatchers deliberately plotted a geographically longer arc to embed the massive aircraft perfectly inside this monstrous river of air. The result was staggering. The Boeing 747 achieved a ground speed of 825 miles per hour, or 1,327 kilometers per hour. The flight touched down in London in just 4 hours and 56 minutes. It arrived an astonishing 80 minutes ahead of schedule, shattering the transatlantic subsonic speed record. The moment the data went public, major media outlets erupted with headlines claiming the passenger plane had gone supersonic and broken the sound barrier. This is a complete scientific myth. The speed of sound at cruising altitude is roughly 670 miles per hour, and the aircraft was doing 825 over the ground. But the plane never broke the sound barrier. Its true airspeed, the speed the plane was moving through the air mass immediately surrounding it, remained perfectly normal, around 560 miles per hour, or Mach 0.85. The air mass itself was moving at 265 miles per hour toward London. The plane was a slow swimmer in a violently fast river. In reality, if a commercial airliner like a 747 actually exceeded Mach 1 true airspeed, its aerodynamic design would suffer critical structural failure. The plane didn't break the laws of aerodynamics. It just took a longer path to surf the sky. This strategy of surfing the sky is so extreme that it dictates the route of the world's longest commercial flight. Singapore Airlines operates flights SQ-23 and SQ-24 directly between New York and Singapore. The straight-line distance is about 9,500 miles, but depending on the time of year, the airline flies completely different global directions. In the summer, the aircraft flies north, straight over the North Pole, utilizing a classic polar route. But in the winter, the dispatcher flips the script completely. The flight heads east, crossing the entirety of the Atlantic Ocean and the European continent. Geographically, flying east over the Atlantic is much longer, routinely exceeding 10,000 actual miles flown. But because the winter polar jet stream is so immensely powerful, the aircraft rides the wind. Despite flying hundreds of miles further, this geographically longer route is routinely up to an hour faster than the physically shorter polar route. For decades, airlines actually wanted to fly these longer, wind-optimized routes, but they were legally barred from doing so. This introduces a fascinating piece of aviation history involving constraints, bureaucracy, and a hidden conspiracy of inefficiency. Historically, twin-engine airplanes were heavily restricted by something called ETOPS, which stands for Extended Range Twin-Engine Operations Performance Standards. Because early jet engines were less reliable, aviation regulators mandated that a twin-engine plane could never be more than 60 minutes flying time away from a suitable diversion airport. This strict safety rule forced airlines into jagged, highly inefficient, geographically longer routes that practically hugged the coastlines of continents just to stay within an hour of an emergency runway. Today, modern aviation engineering is vastly superior. A modern jetliner like the Airbus A350 operates under ETOPS 330. This means regulators trust the aircraft to fly safely on a single engine for a staggering 330 minutes away from any diversion airport. Ironically, this modern freedom from the coastlines allows dispatchers to plot geographically longer oceanic routes deep into remote airspace, specifically to chase off-path jet streams, resulting in much faster arrival times. But engine reliability wasn't the only thing holding planes back. There was also a bureaucratic stranglehold on the sky. For over half a century, Air traffic controllers managed the immense volume of aircraft crossing the Atlantic via the organized track system. This was essentially a rigid, invisible highway system in the sky. Airlines were strictly forced to fly these exact tracks for the sake of air traffic control safety and separation. The problem was that these invisible tracks were rarely optimized for the day's specific weather patterns. A dispatcher might look at the weather data and realize that by flying just 50 miles north of the track, they could catch a massive tailwind, arriving faster and burning less fuel. But they were forbidden to leave the track. It wasn't until March of 2021 that aviation authorities in the UK and Canada finally allowed airlines to fly what is called OTS nil. For the first time on certain days, the rigid tracks were deleted. Airlines were allowed to fly wherever the winds dictated. The subsequent data revealed a shocking truth. Air traffic control bureaucracy, not aircraft capability, had been artificially slowing down flights and increasing global aviation emissions for decades by forcing planes onto shorter track distances rather than allowing them to fly the longer, faster wind routes. Beyond massive jet streams, there are even more obscure, highly niche anomalies in the atmosphere that make a longer path the faster choice. One of the strangest is a phenomenon known as atmospheric gravity waves. These should not be confused with the astrophysical gravitational waves produced by colliding black holes. Atmospheric gravity waves are massive, invisible ripples in the air mass. They are created when high-speed winds are forced violently up and over massive mountain ranges, like the Rockies in North America or the Andes in South America. The air bounces over the peaks and continues to ripple for hundreds of miles downstream. Advanced automated routing software and experienced pilots will intentionally deviate miles off a straight-line course just to surf the upward-moving phase of one of these atmospheric gravity waves. By positioning the aircraft in the rising air, the plane generates lift essentially for free. The engines don't have to work as hard to maintain altitude, which significantly reduces aerodynamic drag. The plane maintains a high speed while burning a fraction of the fuel, making the longer, wavy route vastly more efficient than flying in a straight line through dead air. Sometimes, however, the detour is not dictated by mountains or jet streams, but by geopolitics. Human borders routinely inadvertently dictate atmospheric physics. Take, for example, the route from London to Tokyo. Geographically, the absolute fastest path between the two cities is a great circle route straight across the vast expanse of Russian airspace. But following the invasion of Ukraine in 2022, Russian airspace was completely closed to many international carriers. Flights like Japan Airlines Flight 44 are now forced to fly completely around Russia. This massive geopolitical detour pushes the flight path either far south or far up into the northern latitudes, over Alaska and the Pacific Ocean. This diversion adds up to 2,000 extra miles to the journey. And yet, there is an astonishing silver lining. Because these flights are forced into the extreme high northern latitudes, they occasionally intercept intense polar vortex tailwinds that they would never have encountered on the traditional straight-line route. These extreme winds allow the aircraft to make up a shocking amount of the lost time. They are flying thousands of extra miles, yet arriving much faster than the pure geographical distance would suggest, proving that even geopolitical speed traps are at the mercy of fluid dynamics. But this reliance on the wind brings us to a looming, highly consequential paradox. The atmosphere is not static. It is changing rapidly. Atmospheric scientist Paul Williams has published extensive, peer-reviewed research revealing that anthropogenic climate change is directly altering the high-altitude rivers of air. Increased thermal gradients in the atmosphere are actively increasing the wind shear and the raw velocity of the jet streams. At first glance, you might think this is great news for eastbound travel, and you would be right. By 2050, eastbound flights across the Atlantic and Pacific will get significantly faster. The jet streams will be stronger, meaning longer geographical routes will be increasingly favored to surf these supercharged winds. But there is a hidden cost, and it is mathematically brutal. While eastbound flights will get a speed boost, westbound flights will face such extreme, punishing headwinds that they will take drastically longer. The jet stream is becoming a brick wall for any aircraft trying to fly against it. You might assume that an extra fast flight to Europe, and an extra slow flight back to America would simply cancel each other out. But aviation physics does not work that way. Imagine a flight that normally takes 5 hours. If a massive tailwind speeds you up, you might save 30 minutes, arriving in 4.5 hours. But on the way back, flying into that exact same powerful wind, your ground speed drops dramatically because you are flying slower. You spend more time in the air. Because you spend more time in the air, you are being punished by the headwind for a longer duration. That headwind might add an hour or more to your return trip. Williams' data proves that the net result is mathematically negative. The time saved flying east will never cancel out the extra time and fuel burned flying west. In the coming decades, airlines will be forced to map out increasingly bizarre, dramatically longer geographical routes just to avoid these supercharged headwinds. The sky above us is not an empty, static void where distance equals time. It is a violently active, three-dimensional ocean of invisible currents, waves, and sheer kinetic force. Every time you step onto a commercial jet, you are stepping into a machine that is constantly negotiating a compromise between corporate cost indexes, geopolitical borders, and fluid dynamics. So the next time you look at the flight map on the screen in front of you and see your plane tracing a massive, curving arc hundreds of miles away from the seemingly logical straight line, know that you are not lost. You are not taking the scenic route. You are witnessing the intricate geometry of flight in real time, surfing a high-speed river at the edge of the stratosphere, proving once